Good day, everyone. I will be giving a presentation about our work on audio auto-tagging as a proxy for contextual music recommendation. This work is supervised by Gail Richard and Geoffroy Peters from Telecom and by Elena Epure from Dataset. And to start, I have to give a bit of an introduction. This is, of course, a part of the MIP-Frontiers network and is done in collaboration with Deezer as the secondment, which is part of this project. The work I'll present is covered in 4 publications as displayed here. I will not have the time to cover everything in there, but I will try to give an overview of the work. So to start, I will state an observation, which is different situations usually require different music. This observation can be backed up by each of our own experience or by reviewing the literature on this domain. And this is also reflected on the playlists that the users create. Often in music streaming service, there are a lot of playlists that are created for a specific listening situation. And we can imagine that the content that the users put in these playlists would be the kind of music they want to listen in these situations. So far, so good. So where is the problem? The problem is, as a service, we have 2 ends. We have the users and we have the service. And the way it usually goes, the users do some interactions on the service through the app. And in return, these interactions could be, for example, looking for a track or asking the service for suggestions or just playing a flow of tracks that the service knows the users would like. In return, the service returns these tracks to the user. This part, the suggestions part that the service do, is where the recommendation systems come in place. However, there is something that the service is unaware of, which is the situations that are influencing the user's listening preferences. The service has no idea what are these situations, but the tracks that the users would like to listen to are being influenced by this situation. And this is the problem that we are trying to solve. How do we make the tracks that the service is suggesting to the users more suited to the listening situation that they are experiencing right now? So to start thinking of a solution, we have to look first at all the data that the service has. It's not unaware of the situation, but it has other data that it can work with. This data is a lot of things. For example, the service knows a lot about the users, their listening history, and their demographic information, such as the location, the age, the information they put into when they subscribe to the service. They have their history, the historical interaction with the service, which is the device data that was sent, what kind of devices did you use, mobile or laptop, what kind of networks, the time they listen to music. And they have, of course, information about the tracks, the listening history of what tracks were listened to by whom, in which playlists, etc. And of course, the content of these tracks. So using this available information, we want to try to come up with a solution to propose better situational tracks for the users. And the way we decided to do it is basically to try to answer 2 different questions. First, working on the tracks, given the track pool or the catalog we have of the service and all the users that are available, we want to predict what are the situations that are most probable to be being experienced when the user would listen to this track. And this is the first part. The second part is we would need to know when these situations are being experienced, so that we can suggest the tracks that we think are suitable for this situation. So to answer each of these 2 questions, we have proposed 2 different systems that that we train to answer these questions. The first one is using music auto-taggers. And as Philippe explained, music auto-taggers are very powerful because they allow for a lot of things such as not only recommendation, but search, exploration. And the second part is proposing a situation predictor, which is using the device data that the service is receiving from the users that are using the app, actively using the app. We want to predict what is the most probable situation for these users now. And putting these 2 together, we can probably propose playlists that are suited to the user's situation. Okay, so this is sort of the end goal. But to start, we have to answer a number of questions so that we could get here. These questions are first, how do we identify the relevant situations for music listening? There is probably a number of activities that the users do. What are the ones that do influence the listening preferences, and how do we identify them? And the second part is, how does the audio content actually relate to this listening situation? Is there something that we can learn from the audio content that is related to these listening situations? Can auto-taggers be employed to just predict the listening situation using the audio content? And now that after we answer this question, we have to answer the second question, which is how does this change from one user to the other? So how can we integrate the user dependency of what each user wants to listen to in this auto-tagging setup? And finally, to what extent we can infer the user's listening situation automatically while they are interacting with the service through this limited device data that we have. Okay, so these are the research questions that we would need to answer to get to this endpoint I just explained. Before we dive into what we did, we have to take a look at the previous work when we started. This is at the crossroad of multiple domains. So there has been a lot of work in general on context awareness and context-aware recommendation, not only in music, but in many fields that are related to, that are influenced by the context. Part of these studies are in the cognitive domain, which usually do user studies covering asking the users questions like what are the listening situations that influence them, what kind of music. They try to see how the music attributes are different between these users and these contexts, which is very useful to understand what are the listening situations that we should go after. And there has been a lot of work in context-aware recommendation systems in music and otherwhere. And we can broadly say that they can be split into either specialized systems that are targeting a specific type of context, like points of interest, location, time. They are not very generalizable, which is something that is slightly unwanted in our case. We want something more generalizable, or systems that try to embed all the contextual information that is available at the service into the sequential model that they already use. And I could say the problem with these models is they have less interpretability and less fine-tuning, because we don't really have something to communicate with the users. We just push the tracks that the algorithm outputs without having a way of understanding what is the situation or why these contextual influences made the system make the decision that it was made. And finally, about linking the context, the listening situations, to the audio, there has been limited work on this task. We have to also get over a very related task, which is audio auto-tagging. And as Philippe explained a little bit, audio auto-tagging is a very popular problem. It overlaps with our case when we want to predict the listening situation from audio, when these tags are context related, such as also the mood and the theme can be considered related to this. But the good thing is there has been various models proposed for audio tagging, and they're being proposed by the day, which is very useful for our case because we can just make use of them. But the case of context is a little different from the case of audio auto tagging in general. There are no data sets that are available with only contextual tags, which we want to study for our case. And there is no distinction between contextual and non-contextual tags in the previous data sets unless you do it yourself. But why do we care anyway about treating the content separately? Because unlike most of the other tags that are only content dependent, that only depend on the content of the audio tracks, such as the genre or the instruments, the context is highly user dependent. So we would need to put the user in the loop when we are tagging each track, because this is the intended listening situation for this user. Okay, so this is just a quick recap of the previous work to jump into what we did. We have 4 contributions in this work. First, we took audio-based context auto-tagging for music track, which is basically trying to translate the current state of auto-tagger models into just a contextual setup. And for that, we would have to solve a number of problems. I will get over it. And then we had a dataset challenge in the collected dataset, which was missing negative labels. This will not be covered because we have limited time in this presentation. And then the third one was how to combine the users plus the audio into the auto tagging process. And finally, how to put this all together with a situation predictor model to achieve contextual recommendation. Okay. So let's first start by audio tagging. Audio tagging is a very popular task. In case you're not familiar with it, basically we want to train a model given the audio content, either as the raw signal or as a pre-processed spectrogram or spectrogram, for example. We want to predict the set of tags. And in our case, this set of tags is the intended listening situation, such as gym, running, work, etc. And to do this, we of course need a well-labeled data set with these situations. So the first question we have to answer is, how do we get this data set? And the answer is, luckily, as we said at the start, users create a lot of playlists that are intended for a specific context. The title of the playlist clearly states it. And through these playlists, we can have a lot of information about the content, the users, the creators, the streamers who listen to it. This is not the first time someone tries to do something with the playlists. Pitchell tried to automatically extract context clusters from the playlist titles and apply it to recommendation settings, and it did improve the recommendation. But when we try to do the same thing, we find the clusters a little noisy, a little unreliable, and we want to produce tags that we want to tell the users. These are the tags that we think express the listening situation you're having. So we want something that is more tangible. So we opted for using hand-picked contexts, but still relying on the playlist titles. And the way we did it is first we selected a number of contextual keywords from the previous studies, as I said, from the cognitive or the context-aware systems. And we just collected a large set of keywords. We're trying to extend these keywords by looking at the synonyms and hashtags that appear frequently with these keywords and filter the non-contextual keywords. And then we limited, for our studies, we limited the number of contexts to the first study, we limited it to the 15 most frequent ones in the DISA catalog. And the frequent ones are counted by how many times they showed up in playlist titles. So how many playlists contained these contextual keywords. And this is the set of contextual, these are the set of tags that we will be trying to predict in this setup. Okay, so now we have the keywords, we match them with the playlist. So any playlist that have one or more of these contextual keywords, we would retrieve them. We will apply some filters, such as removing playlists that contain the same artist or the same album, because it could be an overlap between the context name and the artist. And finally, we would fetch only the tracks that showed up in at least 3 contextual playlists of the same context, meaning the same track showed in the same context in multiple playlists. And this is to have more confidence that this track is indeed associated with this context. And then we would have our data set. We can label them, each track that appears with each context that they have. So we collected the data set. It was quite unbalanced because there was there was different popularity for each of these classes. We balanced our data set to have the same number of tracks for each class. And finally, we had around 50,000 tracks labeled with 15 contextual tags. And this data set is, we published it for future work. And the link is here. And then the next thing would be to take a look at this data set just as a sanity check. We want to see what kind of contexts have tracks that overlap together a lot. And this can tell us about this procedure, if it's sort of reliable or not. So we take a look and we find that indeed there are some patterns that make sense. For example, club and sleep rarely happen together, which is something we would expect. They are 2 extremes. Dance and party happen a lot together. Relax and sleep, sad and sleep happen a lot together compared to the other contexts, which means that this pipeline indeed reflects what we would want from this context. Okay, so now that we have a data set that's reasonable, we can proceed to try an auto-tagging model. And we tried a state-of-the-art auto-tagging model, at least at the time that we did this experiment, which is a model by Choi, convolutional neural network applied to the millispectrogram. And we trained this model on our new data set, and then we tested it on the new data set, of course, after we did the proper splitting with no artist, with a lot of criteria. And we looked at the results. And the results at first are slightly encouraging because it's not totally random. The auto-tagging model is indeed capable to learn to distinguish between different situations. However, it performs much better on certain situations than others. For example, party and sad are pretty high compared to other situations such as car, night, and work. And this raises the question whether these situations are more user dependent compared to some others that would have a uniform music style that doesn't really change between a lot of users. So this makes us proceed to the next part, which is how do we integrate the user information into this model and make the predictions more personalized. Okay, so we will jump to the third part straight. I'm skipping the second part. The third part is the User+Audio approach. So here we want to build a user-aware auto-tagging system for the context tags, the same context tags that we have. Okay, so we will need a new data set because our previous data set only had the track context information. And again, we will rely on the playlists that were created by the users. But this time we need to include the users. So how do we include the users? We include the users by looking into the creators of the playlists. So basically we have, again, the same playlists that have contextual keyword and, oh, sorry, hi, sorry. Okay. we have the same playlists that have the same contextual keywords, and they are created by different users. And this creator would be the representative of the user information that we want. So this user created this playlist. Indeed, they want to listen to these tracks in this situation. And using this, we would have a new data set, but this data set is a little different. Now we have a user track pair. We don't only label the track, but we label the track with the user with their intended listening situation. There is something I will briefly mention here, that due to this new criteria of including the pairs, most of our data was single label. So this model was transformed into a single label classification rather than multi-label. There are a lot of details that should be went into here, but I will skip them because of the time. I will just jump straight into the dataset. We collected a dataset now of 180K samples. We also used the tracks that had at least 3 different contexts, meaning that the same track appeared in at least 3 different contexts by 3 different users. And in this way, we can measure how we can learn each user's intended use for each track differently. And again, we did the splits, and we published our data set, which is available here. And these are the stats about the data set. So we jumped into the model. How do we extend the model? The way we extended the model, this is the original model that we used earlier by Choi, the four-convolutional network applied to the mil-spectrogram. And the way we did it, and what we did, is to add a new branch that processes the user information. And how do we present the user information? We present the user information as the user embeddings, which are computed through the matrix factorization of the user's trig matrix. A very common way to represent the users through their listening history. And we join the output of these 2 branches to make the final predictions. So there's also, again, a lot of details into the evaluation that we did, but I will jump straight into one portion, which is just a compact summary of all the results. And basically what we found is indeed that including the user information improves across all the evaluation metrics. This was also coupled by another study that did a very similar thing on the moods, and they got the same results, also published in the same conference in Izmir 2020, which indeed pushes us towards using a personalized auto tagger in the cases of contextual tags or intended listening situation or moods, or depends on how you want to phrase it. So now that we sort of have a prediction, a music auto tagger that is user personalized, we will just need to develop a situation predictor that tries to figure out when this situation is happening. And for this part, it's first, we have very limited data. So this is one point. And the second point is we want this part to be quite fast, because it will be running all the time when the user is just interacting with the service to predict what is the most probable situations now. And so for this case, we tested with different models, starting from decision trees, KNNs, and finally XG Boost. The results I'll present will be for the XG Boost because it was the best and most consistent model. But before I get there, I have to talk about, again, the data. So now how do we get more data about the device data or the stream data of the users? Again, we will rely on the playlists. But this time, we will not consider the creator of the playlist. We will consider the people who listen to this playlist. And now we are assuming that people who listen to a playlist called gym are probably in the gym. It's an assumption we can't validate, but it's what we will be working with. And the stream logs of all these users include a lot of information. Of course, we have the listening history and the demographics of each of these users who listen to these playlists. And we have the tracks that they listen to from these playlists. And we have the device data associated with each stream that they listen to while they're listening to this track within this playlist. So to give an example, if we have 2 playlists, again, gym, now it's listened to by user A, not created by user A. And the same for work, we will have a data set that looks like this. We will have a triplet of the track, the user and the device data associated with this listening stream, tagged with one intended listening situation, which is based on the playlist title. This way we can collect our data set. And this time, we tried something different. We tried to do an incremental number of situations just to observe how increasing the number of situations to be predicted would affect our capability to do it. So we opted for 4, 8, and 12 incrementally added situations. These will be our tags that we are trying to predict. And then to talk about the device data, what are the device data that are associated with each stream? Not a lot, but we have the time that this stream happened, the day that either the day of the week or the day of the month. We have the device, which could be, for example, the laptop, the phone, a speaker. the network, which could be cellular, wired, or Wi-Fi. And then we added this circular representation of the time of the day to account for the circularity in the time of the day. It's quite limited data, but it's what we have. And then for the user information, we have the demographics, which is the age, the gender, and the country, done when subscribed. And again, the same embedding is computed through the matrix factorization of the user's track history. Okay, so we collected, and again, a new data set. Now this new data set, we collected from 2 different locations, France and Brazil, because first they are in 2 different time zones and in 2 different seasons, can allow us to see how this situation prediction can generalize on different locations. And we collected it for the period of August 2019 before the COVID. And again, these are the stats, and the data set is available online. So we will jump to the evaluation protocols. I think I'm time. Basically, we try to test many things on how these 2 systems can be used together in a real setting. And the first one was just testing the system generalization of whether we are actually learning, we're trying to learn by doing splits that include only new users in the testing set or new tracks in the testing set. This doesn't apply to the situation predictor because it doesn't depend on the track. And then an intended use case, which is basically we are not restricted to only new users or new tracks, but we make the split such that we have only new user track pairs. And then finally, a recommendation scenario where we apply a recommendation algorithm. But the way we apply this recommendation algorithm is first, we are applying it only on the situational sessions. Situational sessions are sessions that came from situational playlists that had a situational keyword in the title. And what we would do is we would pre-filter the potential tracks that this algorithm can retrieve tracks from based on the tagged situation. And in this case, we don't do a situation prediction. We assume that we already know it because we already know it from the playlist title. And we only employ the music auto tagger to tag the tracks with this for this user and apply the recommendation algorithm, which is COSRNN. It's a state-of-the-art recommendation algorithm proposed last year. And we would want to see how this pre-filtering would improve the recommendation performance. Okay, so I will briefly take a look at the performance of the situation predictor. And basically, the situation predictor is pretty hard because we have very limited data to predict from a lot of things. And we can see that in the cases of a cold user in 12 situations, we can only predict a quarter of the situations correctly. It increases when we have seen the user before, but it's quite a lot of room for improvement. The good thing is this situation prediction has, I want to say, a hack, because the way you would normally use this in a streaming service is you would show multiple suggestions for the user of what we think the situation you're listening to is. Each of these suggestions is linked to a playlist that is made of the situations tagged, of the tracks tagged with this situation. But we can show multiple proposed situations at the same time. And we can just assume a number, which is 3. 3 is around the number of carousel icons that show up when you open most of the streaming apps at the same time. They will all have the same priority because they are all displayed at the same time. And in this case, we can get much better performance because, of course, we have more room to be wrong. This is a nice utility. Moving from here, I will move to the joint evaluation. And basically in the joint evaluation, what we try to do is for each stream, of course, we had sorry? Okay. Of course, we had the device information and we had that, the track information. And for each, we try to predict the situation independently. And what we are looking for here is the overlap of the correct prediction of all of the streams in our test set. And we get multiple varying performance, of course, based on the split and based on the number of situations. As the number of situations increases, it gets much more complicated. Of course, if we have seen the user of the track before, it gets a little better. There is a lot of individual differences between each case. What I want to say first is the appealing performance of only fewer situations, which is of course expected because we have less to choose from, can be somehow achieved by just involving the user more in this whole process. For example, while inscribing or at the start, asking what are the situations that this user, are likely to experience. So for example, someone who doesn't run doesn't need to be considered for a running playlist, etc. This is also another specific customization that we can do to improve the performance of this overall system. Finally, I will take a look at the recommendation scenario. When we employed a recommendation algorithm in both cases, with no filtering, means that it can retrieve tracks from the whole pool of tracks in the catalog, and pre-filtering only the tags that are tracked with this situation through the music auto tagger. And we see that actually the pre-filtering improves across almost all cases, which is quite encouraging to use in a real case scenario. So if we want to stress on how we could do something like this in a real case scenario, we have at least we have a blueprint of how we can do something like this. We would basically generate situational sessions when the sessions are happening. And the way we would do it is first we would have a background computation. The music auto tagger would be running to auto tag all the tracks for all the users, but this will happen only once. And now we have the tags associated with the user tag pairs forever, or at least for this time period. Maybe we will need to update them. And then we will have real-time computation, which is this lightweight situation predictor is running, continuously running to predict the potential situations for the active users when they are interacting with, when they open the app, for example. And finally, if the user indeed finds a suggestion of a situation they are experiencing, they can just select this situation. And in this case, a playlist made of the tags of the tracks tagged with this situation for this user can be displayed to the user. And we can even add another layer on top of this where a recommendation algorithm like we did can be applied only on the subset of tracks that are tagged with this track. This is quite cool because first, this is much more interpretable. We are telling the user what is the recommendation algorithm thinking that it's doing, what we think your intended listening situation is, and what tracks we think you would like. It's more personalized because we get different predictions for each user independently. And finally, it's lower risk because we don't just push the recommendations that we have to the current session or to the flow or to the user directly, but we leave some space for the user to actually verify this somehow. Okay, so I think from here, we can take multiple, there are multiple paths to extend this work. First, as I briefly said, we had a setup that was the User+Audio Approach was a single label. This is because of the dataset restriction that we have. Our dataset was only single label, but in reality, one user could use a track in multiple situations. So this would need to be extended to multi-label setting. We would need to, all of our evaluations so far was A/B testing, and it was based on historical data of users actually listening to playlists with this situation. We couldn't verify this, so we would actually need to test this in a real life setting through A/B testing with real users and see how it would actually perform in real world. And through this, we could also collect a cleaner data set without a proxy through the playlist titles, but through asking the users directly. And this would make a much cleaner data set to work with. And finally, so far we have been working with a subset of context that we some sort of defined it ourselves. But in reality, we will need to extend this to all possible contextual uses. And this is quite challenging because there is a lot of intrinsic relationships between these situations. For example, sports-related situations should be grouped somehow together, but maybe they split a little bit differently between each user. So a hierarchical representation of situations could be much appreciated, and an extension to more possible situations that are not just based on the most frequent keyword in the playlist that we have is also very appreciated. So I think that's it for me. Thank you very much. And this is more of this is the reference.